हाँ but Hello, everyone. Good morning. I immensely welcome you all to the day 2 of International Conference Earth Sense 2025. We are proud to share that Earth Sense 2025 is technically sponsored by IEEE Geoscience and Remote Sensing Society and financially supported by GRSS Subcoordinates, IEEE Dataport, TCS Research, Urban Kissing, Knowledge Partners with a Development Seat and ISPRS, and finally Media Partner with Coordinates as Media Partner. A heartfelt thanks to all the sponsors for making this possible. Now, it is an honor to have our esteemed guest, Dr. Annabella, with us today. And with me today, I have Temi as my co-host. So Temi will take the honor of introducing her.
Good morning, everyone. I am Temi, AI co-host for the Earth Sense 2025. With immense joy and gratitude, I welcome you all to Day 2 of Earth Sense 2025, hosted at KLH, Aziz Nagar campus. Dr. Annabella Farron. She holds a PhD in space applications for early warning and response to emergencies from the National University of Córdoba and CONAE, Argentina. Dr. Farrell has served as head of the master's program in spatial information applications at the Village Institute and currently works as an adjunct researcher at CONICET and professor at the Village Institute. Her research focuses on remote sensing of environmental quality indicators such as water and snow, contributing to the Sustainable Development Goals. She is also an associate editor of IEEE Geoscience and Remote Sensing magazine and an early career member of GeoAquaWatch. We are truly honored to have Dr. Annabella Farrell with us and kindly invite her to share her insights. We are deeply honored to have her share her insights with us today. Ladies and gentlemen, let's put our hands together. She now takes the stage to deliver her inspiring keynote address.
I invite Dr. Annabella to the stage.
You want to stop for this great organization. Well, today I will talk about the use of remote sensing to monitor water quality indicators and water resource management by using remote sensing technologies. You can. Okay, as you can see there, I belong to more than one institution. That is Woolwich Institute, Geoscience and Remote Sensing Society, CONAE, that is the Space Agency of Argentina, and CONICET. Okay, the outline of my presentation is first to introduce, I cannot see, and the first is to introduce my workplace and my work group, the international, national, and local context of the work I will show you today, some concept of remote sensing of water quality, the study area, methodological approach, and guiding question. Then I will show some results regarding the spatial analysis, the temporal, and the spectral one. And then some lessons learned and future perspectives. It will change later. Okay. Well, thanks. First of all, I want to introduce a little Geoscience and Remote Sensing Society. It has more than 4,200 members in 94 countries and 79 champions all over the world. Here in India, we have a very active one. As you can see, all the people that belong to this society study remote sensing applied to land and surface processes, cryosphere, atmosphere, solid earth, mitigating natural disaster, among others. Also education and standard and policies. You can see here the map, and really I encourage you to belong to this society because in my personal experience, it really improves your careers by promoting conferences, summer schools, community study groups, among others, and publication, of course, high standard publications. Well, my workplace is that what you can see there, my institute, Woolwich Institute, is inside the National Space Commission of Argentina that it was created in 1991, and that it was the ground station. But my institute is also, also belongs to the National University of Córdoba, that is the oldest in Argentina and the second oldest in Latin America. We have more than 1,066 students, 15 faculties, more than 100 centers of research, 70 museum, hospital, laboratory of blood products, very important for Latin America, astronomic observatories, natural reserve, and media. So both together think about making and funding a research institute for applied space science. So in 1997, the Institute of Woolwich Institute became our space, and it belonged to the Argentina Space Agency, also to the university, with the great support of the ACE, Agencia Espacial Italiana. So the mission of the Institute is to research, develop, and training human resources in remote sensing technologies applied to land, ocean, and atmosphere challenges. We are focused on Pacific use, interdiscipline, and transference. We have 2 master programs in space application and also in space system, and 1 PhD in space systems, and we give support to CONAE projects and government and private projects. All the work I will show today was not done only by me, of course. We are a big group of PhD students, postdoc, and bachelor student, and another scientist, of course. Marcelo Escabuso was the head of the institute and is my mentor also. He's a physics. I am a chemist, a physical chemist. Then we have environmental management girls and boys, geographers, engineering, chemistry engineer, physics, biologists, geologists, mathematician, and expert in renewable energies. So the topic we study is the environmental problems. I don't know, doesn't, okay, so here is our approach, how we study the environment. So we perform laboratory measurements. We have an optic laboratory and a small chemical laboratory. We also go to perform field campaigns with a field radiometer, that is an instrument similar to those one installing the sensors on board satellites. And we also perform the data processing and modeling, big data modeling. And of course, we collaborate with national and international institutions. Yesterday we heard Alejandro Freri, that is one of our closest collaborators. Although we are not expert in SAR, but some of the studies we perform with him. Sorry. Here. Well, just to remember, I will talk today about water resource. So Water reserves cover approximately 70% of the Earth's surface, but almost all the water is ocean. So I like to put this phrase that say, how inappropriate to call this planet Earth, where centrally is ocean, no? And from the ocean, from all the water over the Earth, 96% of the water is ocean, and then only 2.5% is fresh water. And from this, some is in the groundwater, some of them as surface water, in the atmosphere, the water vapor also. So we are focused on the lakes and rivers that are a very small part of the water available on the Earth, like fresh water. So it's very vulnerable to pollution. And here I put some problems that can be monitored by using remote sensing relating to quality and relating to quantity. Pollution of rivers, pollution of coastal and oceanic waters, algae bloom in lakes and coastal water, and one of the main problems is harmful algae bloom called AHB and others. Not all the pollutants can be seen by satellites. They need to be optically active. Regarding quantity, you can see we can monitor floods, drought, and overexploitation of aquifer, also by mining, with INSAR, for example, technologies. Because when you explode a lot aquifer, the land subsides, and you can monitor that also. Well, the framework of our work is the context of SDG 2030. And you can see in September 2015, 170 countries around the world met and sing this agenda, yes. And this agenda is very important because it doesn't talk only about natural hazards, but also about social, and integrate the social aspect and the nature aspect. Apart from that, we have 17 objectives, but we have 167 targets or goals to be a specific target is the name. As you can see, today we will talk about clean water and sanitation, but also about partnership for the goals. And this conference is going in that direction. We are joined between different private and public institutions and different countries to achieve the goals. Well, I do some here. As you can see, this is the objective 6 and the specific objectives and their target. Today we will talk about proportion of bodies of water with good ambient water quality conditions. And we also study a lot change in the extent of water-related ecosystem over time. I won't show so much result about this. I will focus on water quality today, but by remote sensing, we can make maps and we can develop this information for the whole countries, and so we will help in our country to get funding to achieve the goals by making this kind of reports. Yes, here are explained the SDG 6.3.2 and 6.4.2, that is the proportion of water bodies with good health conditions. So we monitor the eutrophication processes and occurrence of algae explosions in reservoirs. We also study the impact of land use, land cover in water quality. We also have studied the Ramsar sites and the evolution over the time, and also snow pollution in protected areas that is related also with the water quality and with indicator number 15 over the land. Here you can see photos taken by us, except of one that is taken by a photographer that is a Ramsar site. This is another important international context. Last year we participated in this workshop in Scotland because we are part of GeoAqua Watch group. We were 45 participants from 5 continents, and we prepared a paper about this that is unlocking the global benefits of water quality monitoring through observation and related to SDG number 6 and some outlines about this. Well, for those that are in the career, in the bachelor career and have not so much experience in remote sensing, I will introduce briefly some concepts that for me are important. So remote sensing is to obtain information from a system without getting in touch with that system. And we are focused on remote sensing from space, having the sensor on board of satellite platform. And here, I don't know. And here are one of the main physical principles involved in this interaction between electromagnetic radiation and matter. We have the reflection of light, it's a physical phenomenon. For example, SAR data are mainly understood by this kind of physical principle. Refraction, that is that the light change the angle of and the wave and the velocity when you change the media. Dispersion, that is like a physical chemistry phenomenon that a little particle became like a source of the light of the same wavelength. It interacts. There are different dispersion phenomena. Absorption is a physical phenomenon that we will see deeply. And emission. Emission is the principle of the light. Each body with a given temperature emits light. And how it emits? We use the Planck law, and here we can see that given a temperature of a body, for example, 6,000 Kelvin, like the sun, you will have a spectrum of emission with a maximum that depends on the temperature. And that is the physical phenomenon we use to study the temperature of the earth, of the temperature of the water, of the ocean. So it's very important, the concept of emission. The light comes from any body that have a temperature in the universe. Here you can see the spectrum of the land, and you can see that the temperature of the land is have a maximum of 10 micras. So if we want to measure the temperature of the land, you go to a sensor center in 10 micras. If you want to measure the temperature of the sun, you need another kind of sensor. Yes? Well, here we have the spectrum, and the electromagnetic spectrum is divided in regions. Here is the visible light region and the infrared. And here you have the window, atmospheric window. You almost always, we choose to put the bands in atmospheric windows to have low perturbance of the atmosphere. But you also have microwave that the atmosphere does not perturb so much, so you can see through the clouds, as Professor Nisa yesterday explained us. Sorry. That is very important and nice to see. Light interacts with matter, changes its state of motion. What the meaning of motion in the matter? Motion can be vibrational motion in molecules, can be rotational motion in molecules, can be electronic motion from one orbital to another orbital, and depend on the light, the interaction will change different motions, depending on the wavelength. So the ultraviolet and visible light move the electron from one level to another. The infrared light will change the vibrational mode, and the energy is quantified. That means that each molecule absorbs energy in specific bands. That's why we can detect them from space. That's why we can know that in Venus planet we have oxysulfur, for example, or different kind of molecules. And the microwave make the molecules rotate. That's why, for example, in SAR data, we can see the water because it's absorbed, because the molecule rotate with the microwave light, but we cannot see the ice. The ice is transparent because the molecules are fixed. They cannot rotate. They not absorb that light. So that is the reason. And if you use X-ray, for example, you also will change electron, but electron near the nucleus of the atoms. So you will be able to know more information, not only the atom, but also the state of oxidation, for example, of that atom and the chemical information. Okay. So here you can see, here you can see an example. Apart from that, only the asymmetric mode of vibration are active in infrared, for example. If you have vibration but it's symmetrically, you won't see any signal. So you can perform quantum mechanical calculation and predict the spectra of the molecules. And here, to summarize, you can see intensity against wavelength, and you can see the emission of the sun and the reflected light of Marte, the planet Marte. And here we can see the concept we saw a moment ago. We can see emission light in ultraviolet wavelength because the hot atmosphere of Marte. Here we see a depletion because the atmosphere of Marte absorbs light in that way in blue. So we see Marte reddish. And here we also see absorption bands due to carbon dioxide. And here is not a reflection spectrum, but it's an emission. Here is the emission spectrum because of the temperature of Marte, and so we can know the temperature of the planet. So that's the way we use remote sensing to get information from the Earth. And all the remote sensing system need a sensor on board a satellite. We have a ground station to capture the information, and also a source of light that can be the sun, or we can have a source of light inside the satellite, like SAR system, and then we have to process this information. Today, there are a lot of information to be processed. That's why data mining and IEEE is so important for us. And the structure of a satellite image is a data cube. Each band corresponds to a wavelength, centered in a wavelength, but it has a bandwidth, depending on the sensors, and you have numbers there. And that numbers, digital numbers, should be converted to a physical variable. That is the most difficult in remote sensing. First to energy, and then to a physical variable. And in remote sensing, it's important to take into account the spatial, the spectral, the radiometric, and the temporal resolutions. You have four kind of resolution. That's four. Well, a brief space mission history. It began in 1946 with the first rocket that took the first photograph from the Earth. But it will be very brief, this part. And at the beginning, there were a career between Russia and between United States. And then the first satellites were built to study the atmosphere and the radiative budget of the Earth. And in 1972, United States launched Landsat. It's a program that has 50 years monitoring the Earth. So we have a record of 50 years to study the landscape and environmental changes. So here we have some of the NASA programs. It increased all the time. Here I put this to know how the amount of information we have nowadays. The same with ESA programs. We have a lot of opportunity to study the land, the ocean, the atmosphere. All I am talking about Earth observation missions. We also have a space agency, smaller, much smaller than ISRO, but we also have L-band SAR satellite, SAOCOM. We are going to launch a Saviamar satellite that is, the scope is to monitor the ocean. And well, we have a history in remote sensing, mainly over ocean systems. Well, here I prepared something about ISRO, but yesterday night a professor gave us an excellent talk, giving us the whole history of this agency, amazing. I look into the official page of ISRO. I found that the first Earth observation was from 1979, And until that, it is record here 44 missions. And now you have NISAR with NASA, that is LBAR and SSAR system. Is the first of its kind in space, and you should be very proud about this mission. I hope you can do a lot of innovation with this. And so, my interest is to study the environmental problems. Well, you have a challenge, and once you have a challenge, for example, climate change, you should choose indicators to study that challenge. For example, if you say climate change, you can choose any indicator, temperature, precipitation, but once you choose it, you can study that challenge by field monitoring or by satellite monitoring or joining both. If you join both, you will have a lot of information to do modeling, validation tasks, multivariate statistics, spatial statistics, change detection. Here you have the problem of punctual sampling and a huge amount of money. And here you have the problem of study the requirements. You need to know the spectral resolution, spatial resolution, temporal resolution, and radiometric. It's not so easy to choose a satellite to study your problem. And so, remote sensing as a diagnostic and management tool. We have space-time periodicity, so we can make change detection. And here I would like to tell you about an example of Mario Molina, that was a Nobel Prize of Chemistry. He's my hero in science. He could explain the ozone hole, but I will make a brief history of the ozone hole detection. By the early 70s, some people was studying the interaction between some fluorine compounds with ozone. And in the laboratory, they could see that with ice particles that are present in the stratosphere, in the clouds, and oxide of nitrogen, the fluorine compounds can destroy ozone. They knew that in the laboratory. The NASA had a mission that was called TOMS since 1979. They used to measure low concentration of ozone, but they flag as anomalies. So for a lot of years, the NASA didn't take into account the data because they thought they were anomalies and they were an error. Then, in 1985, the British Antarctic Survey reported a decline in ozone concentration but measured on the ground. And so they can discover that the ozone hole really exists. So NASA reprocessed the data. NASA reprocessed all the data that were flagged. And during the springtime in the Antarctica, because of Antarctica is a round continent, you have like a vortex and you have a behavior of a hole in the stratosphere. And so they could show that the ozone was, the depletion on ozone hole was real. So they won the Nobel Prize, 3 scientists, and Mario Molina impulsed the Montreal Protocol that was signed by 197 member states. That is the great international environment agreement in the history. And that is a signal how remote sensing can help to manage global environmental problems. Okay, but the problem of remote sensing is the inverse problem solving that is not easy at all, is to transform the geophysical variables from radiation to data information. Well, just to show the exponential growth of remote sensing applications to monitor water reserves, here I had only this kind of information from a paper of 2019, but we still have a lot of innovation in the matter. So I put this graph that it shows the exponential growth. And today now I will talk specifically about eutrophication problem. What is the eutrophication? All the waters turn into plain over the years, mile or million years. But now it is exacerbated by nutrients. the algae need sun, need light, and need food to grow. Food is carbon dioxide that you have a lot, nitrogen and phosphorus that are limiting the reaction. So if you put a lot of phosphorus and nitrogen, you will have a rise in phytoplankton, you will have a biodiversity loss, and then you will have anaerobic degradation at the sediment, consumption of oxygen, and you can see green waters and fishes death. That is a problem we have globally. Well, so I will show a study case in Córdoba because the government asked our space agency to monitor the water quality because of this problem. In summer, the water is stratified, so we cannot mix it. And so we have an algae bloom event. And this is a reservoir that was the largest artificial lake in the world in that time, 1888. So it's a very well-studied reservoir. The province includes some mitigation strategies like artificial aeration system to break the stratification of the lake and new wastewater treatment plant. And they asked CONAE to monitor through satellite. So the idea is to monitor of sanitation and control policies, study the impact on land use, predict active algae bloom events, among others. The first thing was to create a monitoring plan. So we chose 8 points. Here the lines in blue are the artificial aeration system to mitigate the algae blooms, and these are the sampling points. We used to go monthly to monitor the water quality. We took a lot of physical, chemical parameters and biological variables. We chose some indicators, as I told. For example, chlorophyll A is an indicator of biomass, and you can, with that, you can calculate the trophic state index. That is a worldwide index. Also, the total phosphorus, the satiety depth, are another kind of index. But chlorophyll is active for remote sensing. Then we also could study the temperature to relate it with the stratification. So here we have our approach. This is a summary that can be applied to any problem, to the air, to the land, atmosphere, what do you like, ocean. So this is our study case, but our guiding question and methodology are, the methodology is to perform field campaigns to collect the data simultaneously with the satellite image or the satellite pass. To implement semi-empirical models can be, for example, based on AI. And to perform a spatial statistic. That is our methodology. The question, where the algae bloom occurs? Where are the pollution sources? And so we need a high resolution sensors like Landsat, Sentinel, or Planet, for example. We can see hotspot, temperature, spatial pattern, etc. If we ask the question when it occurs, how is the dynamic, we need a high temporal resolution mission. So we will look for another kind of satellite with high temporal resolution, like Terra, Aqua, Suomi, GOES, or Sentinel-3, for example. Daily algae bloom detection we can do with that. We do, it's not daily. And what? This is the new era of hyperspectral images. Now we are in the new era. So you can ask what are there in the lake? Which kind of algae we have? Are they harmful? That kind of question can be answered by spectral data. So we use Prisma, EnMAP, or PACE. For example, there are hyperspectral satellites. To see, well, just to show you the difficulties to study water quality. Here you only have field data. And you can see in the X way, you can see the variable I mean the date, and in the wave, the variable. For example, temperature, you can see that it's almost the same of a scene function, very periodic. And another, all the behavior are periodic, but not so clearly. And you can see a lot of variation during the year, maximum in summer, minimum in winter. But if you measure the chlorophyll A during a day, you will see that in the same site, you have very large changes because the algae grow with the sun and goes down. So you will have a lot of error when you calibrate the satellite image because you measure at different time of the satellite path in one morning. So you have a lot of source of error. So when you can detect changes, spatial changes with field data, it's very difficult. The box plots are all the same, more or less. You cannot detect the effect, for example, of artificial aeration, that are the red arrows. So we could understand that with the artificial aeration system, the chlorophyll A was less by doing a lot of analysis of 400 derivatives of oxygen and temperature data. It was very difficult in that moment, but by using only one image, satellite image, we could make a statistical with more than 400, a pixel with 400 data, we could make a statistical and to compare zones. So here you have the NDVI, that is an index, a spectral index, and we can see that before the diffuser installation, we have greener that side, and after we have less green. So we could achieve a statistical with significant difference by using satellite. And we could not do that with field campaigns, 3 years of field campaigns. So that we can see the strength of satellite data for these purposes. And here is a schematic. When you don't have, when you have a stratification, you have depletion of oxygen in the bottom and the phosphate release because the iron reduce and release the phosphate. And when the artificial aeration is working well, the phosphate that are the food for the algae remain in the bottom. We could see by satellite. Now I will go faster to show a lot of examples of our applications. For example, the temporal analysis. We only had 1 pixel in the lake because it was a big pixel of MODIS, and we built a temporal series of 20 years. In that moment, less year, but now we had 20 years. So as you can see, MODIS data have the red band and the infrared band, and with that we could make an algorithm to retrieve chlorophyll A, and we could build a temporal series of chlorophyll A for that lake. All the dots are chlorophyll A. We could model this by using harmonic approach, yes, harmonic function approach. And we wanted to say when our lake was eutrophic. By reading bibliography, all the thresholds were fixed, and our lake was all the time on bloom, and that was not correct. So we proposed in this paper a dynamic threshold, yes, and it was very welcome. And well, we use it to detect the anomalies by this dynamic threshold built with HANS, harmonic analysis time series. Well, then we implement this to retrieve the trophic state of the lake in an operative system for our province. Made by our master students, they implement the algorithm that we developed, and then the government could know the trophic state daily from satellites. And then we continue for more information using Sentinel-2 ESA data. And we perform a semi-empirical model based on infrared and red data, and we could understand a lot of things. We could understand the slope of chlorophyll in each point of the lake. We could see the seasonal patterns. We could see the effect of artificial aeration, different things. We also could see the effect on winter. On winter is worsening the lake along the time. It means that the lake is worsening all the time because winter, all is mixed and we have like the stationary behavior. Well, we could finish that. Then in another lake, we didn't have a good algorithm for chlorophyll A, so we use a green index NDVI for monitor the lake. The NDVI index should be negative in water, but if you have a lot of algae, it could be positive. So this lake is another lake. You can see the watershed and how the land use was changed in the years. And we can see that the NDVI was negative until the last year that became positive. And we could attach statistically the behavior of the land use and the water quality of the reservoir. Now, we are trying to do a very difficult thing that is forecast algae bloom. It's not easy. We couldn't do it by multiple regression algorithm. We are using egg boost approach, machine learning, and we are putting an entrance different weather variable. For example, temperature, wind in the surface, precipitation, and chlorophyll A measured in 1 day. Yes, retrieved from the satellite, from our algorithm. So we use ERA5 variables. That is a reanalysis model from ISA. Here you have the variables, and we also consider lags, 1 week lag, 2 week lags in the model. And we obtain very good results. Here we can see the future importance. We can see the real value and the predicted in red. And so we have a coefficient determination of 0.92 and an error of 7.5 milligram per meter cubic. That is very, very good approach. It is not published yet. It's ongoing. We have finished this publication, this work. Well, now I will introduce to the new era of hyperspectral data, the new thing we are doing. In Argentina is a vacancy area. You can see China is the leader and United States, also Germany and Italy because they have missions, but you don't have a lot of work related to water quality and hyperspectral. It's a very promising field. Here you can see a few works in Argentina. Here you can see Prisma signature or spectral signature and Sentinel spectral signature. Here you have 12 bands and here you have 234. In total, here we cut it 900 nanometers, but it lasts until 2,500 nanometers, and this until 2,000 nanometers. This is multispectral and it is hyperspectral. But well, I am a chemist, so I wanted to understand the spectral. So these are, we have our field radiometer in CONAE. We took field data of the lake. This is average behavior. This peak is very predominant and is related to algae, the presence of algae, but we want more. We want to see if we have cyanobacteria that can release toxins or we have another kind of algae. Well, so we perform experiment with algae, cyanobacteria in the laboratory, reflect an experiment, absorption. We prepare the culture of algae. Here you can see the cultures, and here are the techniques we have used. I'm sorry. We use absorption that I showed before, fluorescence that I didn't mention, but it's a phenomenon that is when you electron go to another orbital, another energy level, it releases a little energy by thermal or by, aleatory release of heat, and then the system releases an electron in a lower energy. If you, for example, the vegetation has chlorophyll, and the chlorophyll has fluorescence. So if you give the vegetation blue light, the vegetation will emit red light. Yes, all the vegetation is emitting red light. And nowadays there are new missions that are building focus on fluorescence measurements, new satellite missions. And the reflectance is what we were seeing until now, reflection of the light. So we perform, sorry, ahí va. Yes, the results of absorption, here you can see in a spectrophotometer, we can put the algae in a cell and we can measure for different concentrations the absorption behavior. And we can see some peaks related to chlorophyll and some peaks related to cyanobacteria, that is phycocyanin pigment. So we have here two pigments. One is present in all the phytoplankton, algae and cyanobacteria, and is the most worldwide used, chlorophyll A. And the other is phycocyanin, is less used, because we didn't have the sensor with that wavelength in 600. This is the fluorescence for different concentration. It's linear, the fluorescence with the concentration, the behavior, so we can make quantitative detection analysis. And here we have the sensibility for different wavelength. Here you have the system, the experimental system, a source of light, another source of light, and the cell to measure the reflectance spectrum in the laboratory. We performed this, and we found very interesting things. For example, for small concentration, you see very well the fluorescent peak. That's why in the ocean, to measure chlorophyll, we can use fluorescence. There are a lot of algorithms based on fluorescence. But in inland water that you have higher amount of chlorophyll, you don't see anymore the fluorescent peak, because the absorption doesn't allow hide the fluorescent peak. And another very interesting thing is the peak of reflectance, typical for vegetation or for algae. It goes to the shift, had a red shift. And this change in the red could be very important when you use different algorithms that are in bibliography. For example, you have in Sentinel-2 a 705 nanometer band, and that band is located here. So if the peak is shift, you will have a lot of error using that band. For very eutrophic water, it's not worth to using the nearer red band. Well, that kind of thing we could study. Then we perform analysis for 4 types of cyanobacteria. We found very different results regarding the phycocyanin behavior in some cyanobacteria and in not. And this can explain why in bibliography some authors have success with the algorithm and another not. So we are deeper in these issues. And if you make a zoom, you will see that for different cyanobacteria, you have slightly shift, and you will be able to detect and to say the different class of cyanobacteria. That is the main objective of, for example, the new satellite of NASA, PACE. Sorry. Then, now we want to know how to compare these spectra. It's not easy how to compare these spectra. So we can use Euclidean distance, we can use spectral angle mapper, we can use both. So we use a metric that was developed by Nida Maruri in 2010 that is normalized, and the sum should be 1 if the spectral are the same. So here is quite difficult to see this, but for 4 kinds of algae and 5 kinds of concentrations, we measure the distance of the spectral. The idea of this is that for the same couple of algae, of cyanobacteria, you won't be able to differentiate always those. You need to know the concentration. I mean, for a different combination of concentration, you can differentiate or not the cyanobacteria. That is a very important issue to develop algorithm for remote sensing. And now we go to the satellite information. We use Prisma, that is hyperspectral satellite from Italy. Through a project, the images are free. Here you have the BIS cube that has 66 bands and the SWIR that has 171 bands. Then you have a panchromatic and the spatial resolution is 30 meters. Here you see the lake with a bloom that day. So I will show you. The first difficulty was to extract the water because, as you can see, the bloom seems grass. So we didn't know if it was land or was water with algae. So we choose an infrared band that is where all the water absorbs the energy, so we can retrieve the form of the lake, the vector of the lake. And then what we do was to draw different index. An index that is based on the absorption peak of phycocyanina. So with this index, we can see phycocyanina presence or cyanobacteria presence. And the other index is the common one used, that is chlorophyll A index. And you can see phytoplankton all over the lake, but only in a few parts, cyanobacteria. The aim of our project is to differentiate cyanobacteria and other algae. We are in the right way. Why? I don't know why it doesn't go. Maybe it doesn't have battery? Next. Well, so then we perform PCR analysis that is very useful for hyperspectral data. With a PCR analysis, we could see three principal components as the most important, and the first five explain the 98% of all the variability. And if you put this component that is the first one, that it remain the phycocyanin index, this that can be associated with the water, with the background, and this that could be associated with other kind of algae. If you put the first component in the blue, in the green channel, the second in the blue, and the third in the red, we can understand very well. Here it seems cyanobacteria, green and cyan. The background of the water can be seen in blue, and the other kind of algae can be seen in red. How we can validate this? Well, we can validate this by transforming the data collected in the laboratory to the signal of Prisma by resolving this equation. For those, we use the response function of the sensor. This function is given by the space agency. This is the response function, this is the response function of the sensor, and this is a spectral angle mapper between the spectral of the Prisma data with the spectral measure in the laboratory of a cyanobacteria. And we see a high accordance. That is a very good result. And then to validate, we use a field campaign. This is the abundance of different cyanobacteria and algae. And we could see cyanobacteria in the points we propose, here and here, and another kind of algae, brownish algae, in the red ones. It's a kind of validation, yes? So these are very promising results. We also use a radiative transfers model to understand this system. So we model the reflectance of cyanobacteria, and we also retrieve the data from Prisma using that kind of modeling. That are physical models. And we also produce web service maps for the government. So all the algorithms we develop we introduce in a system that is operative and give periodic maps of water quality. These are clouds, that's why are blank. Another kind of study or system, with, for example, by Victor Gauto, we are studying Paraná River, very turbid to clean water, and you can see Prisma data from this one to this spectrum according to the turbidity. We are developing this kind of algorithm. And also he will use machine learning to predict not only the water quality, the turbidity, but also the flow. Another PhD student is focused on the impact on land use on water quality in a river basin. So we could, can you help me? We could make a research by analyzing the water quality index in a river and the impact of land use. And the novel aspect of this paper is that the period of the crops, winter crops or summer crops, interact with water quality differently. You have different amount of nitrogen, ammonium for different periods of crops. That was the main achievement of this work. And well, this is Juliana Beltramone, that she's studying snow pollution. Pollution, the spectral of snow changes with two things, the grain size and the impurities that has inside. So it's very difficult to retrieve impurities because it's also changed with the grain size. So we go to make field campaigns, we collect the snow, we make experiments, we measure the physical properties. We study the snow by SAR. Here you have the retro dispersion for different polygons with different slopes, and we can see the wet, the melting point. We make a paper with derivative to detect the melting point, and now we have another one that was presented in IGARS using horizontal visibility graph. That is a very promising technique. And here you have optical simulation, radiatory transfer simulations for different impurities, pure snow and different impurities, ashes, black carbon, dust. So the idea is to think in a mission to measure snow pollution. Here we are in the snow. Here you can see something reddish because we found red algae in the snow for the first time in one national park of Argentina. We are studying this data. We have here, we put black carbon nanotubes, nanocarbon, to simulate black carbon and to have some spectral. And here you have the experiment. And well, then we took the sample to the laboratory. Here you have a impurity collected in the snow. We make the Raman spectra. The Raman spectra is similar to infrared spectra. We were looking for black carbon, so we should look for carbon-carbon stretching vibrational mode. We found the stretching of graphite carbon. Here we have the nanocarbon made in the laboratory, and the red one is the one collected in the snow. So we could find black carbon in the snow and measure in the laboratory. And with satellite, we can see this difference is attributed to a wildfire, and the ashes of the wildfire goes into the snow and download the albedo of the snow. We could also measure, and here a SEM is a SEM data that is a microscopy, electron microscopy, to see the ashes, black carbon. And so, well, we are just finishing. 10 minutes, no? So now, sorry, I get anxious. So the conclusions. Just to, I gave a brief overview of the thing we are doing in our laboratory by field campaigns, numerical modeling, semi-empirical estimation, machine learning approach, and as conclusion, satellite monitoring is a complementary tool to evaluate water quality. it's important to see that it's complementary. Although it presents challenges to interpretation, the integration with other technology is crucial for sustainable management. Here I put atmospheric condition because in water you should do very well atmospheric correction. I didn't mention in this presentation. The freely available spatial information for Earth observation satellites make possible to evaluate the influence of anthropogenic and natural impacts on the acceleration of eutrophication. And we have a new generation of satellites with hyperspectral sensor, open a new era of possibilities. Well, the future perspective is to detect cyanobacteria, to make a map of algae species diversity, and to retrieve pollutant from snow. We are collaborating with Sabiamal calibration campaigns, with another national and international initiatives. I would like to collaborate also with people from here. We want to advance in the development of early warming algae bloom, as I show. And the last one is to integrate remote sensing and nanotechnology to improve detection and understanding of a pollute system. So now we have an ongoing project that is focused on nano-remediation based on nanoscience. I will go to Barcelona 6 months to work in this project. And to track the impact of nanophotocatalysts with satellites. The idea is to merge satellite, artificial intelligence, and nanoscience to have a solution for these kind of problems. That is the last we are doing. To finalize, environmental safe means social equity and health environmental. This is a picture of a famous painter in Argentina, and this was the river most polluted in the world. It is located in Buenos Aires. And this painting was done in 1961. This is a boy swimming in the garbage. So, well, just GIS and remote sensing make us the possibility to visualize the problem and to find solutions. Thank you very much. Too long.
Thank you so much, Dr. Annabella. It was so insightful and informative. And up next, we are pleased to welcome our sponsor, Urban Kissin. It is my privilege to introduce their work and their representative, Mr. Praveen. With us today, we have with us Urban Kissin's specialties in urban farming, horticulture, farming, and indoor farming. So today, to represent Urban Kissin, we have Mr. Praveen with us, their chief AI scientist with vast experience in AI, signal processing, and machine learning applied across agriculture, healthcare, energy, and more. Now, Temi will take the honor to welcome Mr. Praveen.
We are truly honored to have him here at the Earth Sense 2025. I now invite Mr. Praveen Pankaj to share his words with us.
Mr. Praveen Pankaj onto the stage, please.
All right. Hi, everyone. I do understand that I am standing in between you and your lunch. So I'll be, I don't know if I can be very quick, but I'll try to do my best to keep everyone engaged. It's more of probably a provocative presentation, if I may say so. And is everyone in the back able to hear me? Like, yeah, okay. So So myself, I'm Praveen Pankajakshan. So I'm a chief AI scientist in Urban Kisan. I'm also a member of IEEE and really honored to be part of this conference. So for thinking about today, I thought, how do I probably like address some, so there is the aspect of academia, there is a lot of things happening in the academia, but there's a lot of things happening in the industry as well, right? So I'm going to bring like, I wear like 3 hats. So I'm going to bring from those 3 hats, right? Like one is despite being in the industry, I'm still associated in some form of the other with academics. So I wear the academics hat. I also wear the industry, and I'm going to give some perspective on government also, right? So I managed to sneak in this presentation, but hopefully it's interesting for you all, right? So sovereign data, let me see if this works. Yeah, this works, okay. Sovereign data, knowledge, compute, and foundation models for the global south, right? So there is a lot of conversations happening around data, models, and compute, right? Before I go to just a very brief about Urban Kisan. So I've been in, my background is AI and machine learning, and I moved to remote sensing a few years back, a decade or so back. But I mean, my PhD was in a remote sensing lab, but I did microscopy. Urban Kisan, we are in the process of, fast accelerated breeding, but not using, but using traditional techniques, right? Like how do you optimize for better approaches for breeding? So we call that as gene rush. Sorry, maybe it skipped one slide. I can't go through the slides. It's not working for me. Can you go back like to the, okay, the next one, please. The next one. Okay, I don't know what's happening. Something has happened. Okay, just go back to the previous one, right? So we were facing some difficulties with agriculture. One is delayed breeding. Anything that takes, in breeding, production of seeds and everything will take anywhere between, 5, 10, 15 years sometimes, right? So, so what we wanted to see is there any way to, breed faster, better protocols for growing and everything, So anyway, we had a lot of things, but there we are in the process of releasing something called as a Farm OS. So it's an end-to-end intelligence system for indoor and outdoor farming. So we were into hydroponics and indoor polyculture and everything, but now we are also moving into the outdoor farming. Obviously, you can ask the question, why am I talking about remote sensing for indoor farming, right? Okay, next slide, please. I am not able to control from here. Okay, it does work. I have to point it in one direction. Which direction? Can you go back? The next slide, yeah, okay. There is, obviously there's a lot of data, and if those who have been working in remote sensing, you might be familiar that there's a lot of data that's there, but most of this data, at least from my perspective, when I was trying to train models and everything, it's been mostly confined to certain regions, like if you look at India, I've worked in sub-Saharan Africa, right? Kenya, Nigeria, and all of that. Data is very sparse, right? And not only that, there is, the data is dark in many of these regions. Knowledge is present, like India is great in oral traditions, but we have not like documented the knowledge, right? So that's a big thing. Compute and models, I'll also come to that, right? Like, but you'll see very quickly. So, but unfortunately, major disruptions that's happening and leapfrog movements can actually be triggered, and innovations can be happening when you look at data, when you say, oh, maybe this is a gap that we have to address, right? So that's not there. And as a result, there are some other things, governance, even AI governance is missing, right? Which is AI governance is largely driven outside many of these global souths, right? So that doesn't have implications for us, right? And the other is environmental implications. Many of these models are very highly consuming in energy. There is obviously algorithm and model bias, right? Next slide, please. What does it mean for a geospatial perspective as well, right? Next slide, please. Okay, let's talk about data set. Okay, I think you must be familiar with all of these data sets. I think you are more expert than I am in this. So I have tried to list some of them, many of them, but you will see that like Let It Be Pastors, Eurosat, SEN 1 to MS, multispectral data, Zuri crop, Braze crop, even the US CDL layer, right? Big Earth Net, all of these are very famous superstars in the data set. But what's common among all of this? These are all data set that you get in the global north, you know. There are some good work happening by Zindi, I think you know, from similar to Kaggle, right? They're doing good work on creating competitions and ensuring that we have like data set also, which is representative from other regions, right? But overall, if you look at these data sets, is mostly in Europe, some in the US. I think USGS has done a good job with the CDL. But where are we in this, right? So it's a huge miss. There's actually like very less amount of data set that you have in ground data, you know. And I've seen also data set for which is coming. There's often a lot of noise in some of these regions, right? Next slide, please. This is a recent, this is just off the press, right? You'll find this in archive. This is from MIT, Sherry Wang, I think you might be knowing. This is a data representation from some of our work, recent work, right? You can see like, this is really data dark, again, with respect to some of the major regions, which we want the data set to be. So this is, you know, a representative of most of the stuff. Again, this is not a criticism of the excellent work that they've done. This crop globe data set is great. But it's a stark reality, right? Like we don't have publicly available data set. And unfortunately, so the models which are going to be trained is also not relevant. Next slide, please. What about storage? Where are the major scalars of storage, right? If you look at cloud computing, right? The yellow is the APAC region, green is Europe. And you see that the most of it is blue, right? The data storage, that means any data you store as a result of computing, storage, processing, results, analysis, insights, all of that is going to stay in data centers outside of where you're located. Many, like for example, I as a company have provided solutions for Africa, India, Asia, and everything. They've all been asking like, where can you store data locally in our country? We don't have data centers there, unfortunately, right? It's very expensive to maintain. Yeah, thank you for, no, you can go to the next slide. I'll be very quick. What about the extreme cost of training, you know, chat GPTs? If you're looking at even geospatial models, right? They're quite expensive, right? And I'll not go into this. This is not affordable for the bulk of us, you know. I'm not even going to the article processing charges with some of these journals also. You know, they're not affordable, right? Come on, next slide, please. Yeah. So as I said, I'm going to be a little bit provocative as well, you know, because it's before lunchtime. What about chips? Okay. So India, as India AA mission, has taken it a responsibility to build its own chips. You know, that's a great thing. You know, one round of applause for the Indian government. You know, but we are going to have like more and more restrictions on the amount of chips that we can import, and they're going to be humongously expensive. Not only expensive, even if you can afford it, it's not going to be affordable. It's not going to be. There's a humongous amount of wait time for the NVIDIA H100 and H200 chips, right? Next slide, please. Okay, all of this now, the most important thing, all of this has implications on the models as well, right? Like, next slide. So let's look at models, you know. Obviously, everyone is talking about foundation models, and I think geospatial foundation models are also becoming very, very important. Let's look at, you know, this is a very famous SITS former, right? Like based on satellite image time series data. It's a very nice article when it came off, based on transformers, combining the idea of transformers when it came. I think it's 3 years old. But there's been like a lot of things which have stood on top of this, right? So the idea is to take time series data, you look at image patches. So if you have a Sentinel-2 or Landsat or something, and you look at the multiple bands, do the usual, the spectral embedding and the positional embedding, right? And then you encode that data set. So you do you know, kind of pre-training and then use it for downstream applications, right? So that's a very common trend that we see these days. But again, like if you look at the data set that it's trained on, it's on Fresno, California, 216 images. The tiles is these 3 tiles, right? What happens? I have seen from the industry where I work in, you know, in agriculture, what do we face right now in the global south? The global south, what we face is during the, and this I'm talking from agriculture perspective, is that monsoon season is filled with clouds, right? We have hardly any data that comes. So if you're looking at 6 months window time, probably you'll be very lucky if you have 1 month of data, right? This is a reality, right? How are you going to do your NDVI studies on it, right? Then the other thing is you cannot work on patch-based studies, right? Your minimum size of a land is going to be about what, 1.2 acres, you know? So how are you going to do patch-based studies? You know, your patch, typically you're looking at this 5x5 patch, that's 50 meter by 50 meter, you know? So that's not going to work, right? Like, so you're easily going to miss many of these lands, croplands. Next slide, please. So obviously, like there are some interesting things which has happened from pixel-based studies as well, right? So this is very excellent work, similar to the SITS transformer. This is the SITS BERT work, but it's on pixel, right? Pixel-based temporal models does make sense for many of these smaller geographies where small-scale land holding farmers are enormous, right? Then Presto from the European space, NASA Harvest is also like really a good model. But all of this, like if you look at the representation, even for pre-training tasks, right? How representative are these of the global south? So what happens, even if you're taking, let's say for samples for training these images, okay? How do you, so for example, they look at NDVI data set, right? They look at land cover data set. So the world land cover data set is coming from the dynamic world, right? We know for a fact that they don't work for India, Asia and Africa, right? Now, if you're going to select samples from that, I can show you images. If you're going to select cropland samples from that, and if you're going to train your model and everything, they are not representative because many of them might be shrubs, grasslands, it might be trees, you know, and mixed for crops, right? And sometimes there's crops and mixed for barren land, right? So all of this is an issue even when you're training, you know, a large model, right? A geospatial foundation model, which, and for us to be sovereign, so, you know, we are talking about chips, we're talking about data set, and we are talking about models. And most important thing is knowledge as well, right? There is a humongous amount of traditional farming knowledge which is there in this global south, which we are also losing on, right? Next slide, please. So there are, I mean, I can go on and on about these geospatial foundation models. There are many coming in every day. These are not representative of the many which have come in. And there are some which have looked at it purely from, if you're doing like deforestation studies, then like, you know, SAT-CLIP, some of these metas, you know, segment anything model, all of that makes sense, you know, if you're looking at it from a computer vision perspective, right? And I'll show you also some early work that we did on Prithvi as well, the NASA IBM model, right? Next slide. But what happens is, what about the agroecological zones, the crop calendars? You know, India, for example, has at least 30 agroecological zones. So are we going to have representative samples from each one of them? No, we don't have. Crop calendars are really missing. Which time this crop is sown, how many cropping patterns you have, all of that is missing, right? And it's very important because if you take a time series data from across the entire year, it's not going to work. You have to have representative samples from when the crop is going sown to when it's getting harvested. And imagine every, you know, 10 kilometers, there'll be a difference. Next slide. Agriculture is not business as usual, right? Like things are changing, but we do have the traditional practices should not be left out, right? This is my hand from my farm, okay? This is what happened in my farm this summer. You know, although we are experiencing extreme monsoons this time, but last summer this was the situation, right? And I follow regenerative agriculture, you know. Next slide, please. And this is the situation globally as well. So there is, obviously people have looked at it more from a vision perspective, right? The SAT MAE, the VIT kind of transformers and everything, they're looking at it. But those wouldn't work for these conditions, right? They're not temporal representative. They are not representative of the kind of topography that we have, all of that. And even if you look at it from a temporal perspective, right? So we need so there are very few data set which looks at, you know, even GRD data set and things like that, right? Even multimodal data. We don't even have good soil maps in these regions, you know. We are probably looking at ISRIC data set as soil maps, but, you know, there is a lot of even SRTM data for topography, right? Next slide, please. So this is where I'll just maybe just quickly shift gears here because I know that I'm also running out of time. We are from the Ministry of Education, from the Government of India, have set up this initiative of creating AI centers of excellence. One of them is in agriculture. Next slide, please. I'm part of the committee. IIT Roper has been selected for the AI Center of Excellence. What we are trying to do is all of these, right? And I think we are ambitious about it. And that is necessary, right? Building right from IoT devices to semiconductor stuff for sensing, for measuring, from livestock to soil to weather, right? If you are talking about right now, we are proud of the fact that there are many AI-based weather things. But you know, the weather that we get in data that we get in India for training some of these models is not hyperlocal, right? How many weather stations do we have across India? And we have the ability of changing. IIT Roper is taking the lead. They are trying to install weather sensors in food delivery bikes, you know? It's very interesting, you know, why not? You know, you can actually now have mobile weather sensors. So innovation is there in India, right? Innovation is there here in Global South. We are also looking at livestock, you know, so hopefully like all of this will actually lead us, not only us, but even Africa and other regions towards sovereign chipsets, sovereign data. And most important thing is we are also collecting knowledge, indigenous knowledge, right? We cannot, for some reason, we think that agriculture should be only about modern practices, but our traditional practices are very, very ecological, climate sensitive and everything, you know, and we are missing that on that. Next slide, please. Yeah, I can skip this. Yeah, it's an ecosystem. So what I've also done a little bit of contribution. I think this is a shameless, probably a branding or marketing slide, if you make it say so. We built a model, large language model called Akshara. It's a very, very small model built on top of Mistral, but for providing advisories for farmers on climate, right? We want to integrate this with remote sensing as well. So that's also in the pipeline. We have already done it. So you can find this model on Hugging Face. If you just type AKSARA, you will find it in Hugging Face. Next slide, please. So this is one work which I was interested in. So, you know, I shouldn't just only like complain, I should also do something about it. So what we did is we actually took data samples from across India, across many of these regions where small landholding farmers are. We took the land cover map, we selected regions which are correspond to those regions having crops, having trees, you know, many of these diverse land covers. And then we built samples and then we trained a foundation model. You know, I can't go into the details of it because as a company, I cannot share all of that. But the idea is to look at something like masked autoencoder. You know, can you like, you know, take image samples, take a clean image, mask, you know, and that's a great way of representative learning, right? I think I can take maybe a full session on representative learning, but one of the idea is to, can you mask some of these pixels, some of these regions, and then try to reconstruct, and then do a downstream task, right? Here, the downstream task that we're interested is in, is actually like reconstruction of cloudy image. These both are not same images. This is the input image, and that's the output image. That's a reconstruction. Can you go to the next slide? Not only heavy clouds, but even where there are hazy regions, right? We are able to, so that's the input image with haze. That's the reconstructed one, right? Next slide, please. This is comparing against the NASA IBM. I think like there's a lot of obviously interest in the Prithvi model, but you can see that the construction is not there. This is very, I've seen it in multiple different foundation models, and it's there are like heavy artifacts, right, from reconstruction. So you need more time samples, you need multimodal images, right, to kind of like, and not only that, I've also tried these models into our applications for crop classification, you know, land cover classification, and they don't work. They don't work, you know, despite it being like, you know, having very high accuracy. But that's with respect to some of these benchmark data sets, right? The problem is we don't have benchmark data sets yet, you know, and there is really a need for building benchmark data sets, benchmark knowledge, right? And so that we can test all of these models and give like a fair, unbiased review as well. Next slide, please. Since you talked about NASA, about Prisma, I thought, why not add this? So I add this like when your keynote was going on. So this was a work on the Prisma data set. So this is in Italy. So again, these are cases where, for our case, we might not have labeled data set, right? So this is a recent work I've just submitted to MDPI sensors. So it's still under review. The idea is, can you use minimum number of ground truth data? Because ground truth data collection is very difficult, right? You have input data sources from some of these benchmark data sets. Can you do a domain transfer, right, to new locations, right? And this is I've taken in Italy, but because Prisma data set is available for some of these regions. So this is hyperspectral data. Can you actually find paddy growing regions, right, using this, but with very, very minimal amount of label data set, right? It's almost like a zero-shot learning here, right? I'll not go into the math of it, but I just added this as a basis to say that you can actually do some kind of tweaking and weak labeling to also overcome of the lack of a label data set as well. Next slide, please. I'm almost done. So I'd like to invite for collaboration. So I'm in the process of building data, knowledge, and everything. So I've open sourced this on my GitHub repository, Agree Data. All the codes, most of the things which I can open source, I've open sourced the code, data set, everything on my repository. So it's very simple, github.com. You can go to Praveen Pankaj. There's a lot of information there. We're also building our own rover. So that's our indoor farming rover system. We're looking at building the vision system and integrating that. It's also a way of collecting label data set from across the globe. Next slide. So I invite collaborators, and these are some references which we publish. Some of our students published. Yes. Next slide. I just want to leave you with one last thought, is that, there are a lot of changes that happen in agriculture, and we are kind of like independent right now and compared to the rest of the world. So we do have like right now we can say if there is any country which is imposing tariff on us, we have the luxury of saying, if you impose tariff, we will go elsewhere, right? One of the major reasons for those tariffs were on corn, right? There was even a statement 2 days back on can India not even buy a few bushels of acre? So the problem is that we are losing our own biodiverse seeds, right? And we have to be very cognizant and very careful of that. So more important for us is our own sovereignty of some of these indigenous seeds, indigenous knowledge, indigenous data, indigenous infrastructure, indigenous chips, right? Enhance indigenous models, indigenous even policies, right? So obviously AI and geospatial is not going to bring a difference, right? All of this is not possible without policies, right? I think that was the end of my slide. If you can go, I don't know if I had any more. If you can add. So that's from my farm, so some of the things. So I don't want to just complain, but I also try to implement it in my farm. So this is a regenerative farm. So you're welcome to join. And that's my last slide. Thank you so much for your time and appreciate it. If you want to connect, I'm available on email or on LinkedIn. So that's the QR code. Thank you for your time. And if you have any questions, suggestions, comments, I'm available now or later. Thank you.
Thank you so much, sir. Thank you so much. You ended up with a great slogan, we cannot change the past, but we can do our future better. All the good works for our nation. It was great. And now, next we have IEEE Data Port session. It gives us great pleasure to welcome our sponsor, IEEE Data Port, represented by Ms. Anjani Diwan, Senior Member of IEEE and Data Port Ambassador. Now, Temi will take the honor to introduce her.
IEEE Dataport is a trusted global research data platform enabling secure data sharing, storage, and collaboration. It offers data assignment for datasets, 2 terabytes of free cloud storage with AWS free integration and open access options. Dr. Anjali Dewan, a faculty member at Bharwati University, Gujarat, is an alumnus of DAIICT, Gandhi, and brings over 20 years of experience in academia and the software industry.
Today she couldn't make out to come here, so she'll be connected us virtually online. So I request the technical team to pray.
Hello everyone. Today we are going to discuss about AI and data management and data sets and how IEEE Data Port is going to help you with this. So my name is Anjali Devan. I'm an IEEE volunteer and professor, and this is a small brief about me. So I'm associate professor and head of the department for CSE Marwari University, India. I'm a steering committee member of IEEE Data Port. I volunteer on different regions and levels of IEEE at section level, region 10, etc. My passion resides on mentoring, advisory on startup, which is related to AI, data science, and emerging technologies. My core research interest area is computer vision, machine learning, and data management. So let's talk about IEEE data. Um, the data code is a valuable tool for data sharing and data management. So first of all, let's talk about IEEE data code, how it does. So IEEE data code is now having more than 9,000 plus data sets and a huge number of global users. IEEE data code basically provides us cloud servers, AWS, where you can share uploading data. We have a web interface through which you can actually manage your data. So what kind of data you can upload here? So it is not just simply data upload platform like other platforms. It is basically a data management platform where you can actually publish your data sets. So when you have a well-curated data set, you can publish your data set with a big one. So as an individual, you can publish your data set. As a university or research institute, you can publish and manage your data. As a government agency, as an industry, as a scholar, and there are so many different uh, ways by which you can uh, manage your data, you can publish it, and share with other users. So, what are the different data set area? Yeah, that is another question which generally people ask. But that, okay, my domain is X, can I submit my data set? So, yes, I think data code is allowing, or it is having a wide range of different domains. So, currently, we have 36 different domain data sets we have. Among that, you can need many utility data like environmental data, sensor data, weather data, agriculture, power, wireless, social science, AI, machine learning, virtual data, spectral images. So there are so many data sets we have. I think data report also supports different type of formats. Like if your data has sensor data, which is in the form of numbers, so you can have page of the website. So here you can see it's a very simple website and everything is on the first page which you can access. So if you want to see some data, so it is not necessary that always you are going to use some data set and publish it. Sometimes we need data set for our research. So you can see or explore different type of data set. The first tab is data set tab. When you click here, you have to enter the keyboard, and based on that, you can get different list of data sets. Also, the front page of the dataset page is having different dataset on the you can explore that also. So in this way, you can look into the different data sets. Now, question arises, can everyone access the data set? So yes, if you are actually with society membership. So here society is e-society, including your censor council, if you are member of censor council, you are member of future society, GIS society, then you can definitely log into your activity credentials. The same credential which you use for activity.org, you can use here. And with that credential, you can access the data sets. So there are basically two type of data sets we have. One is open access, second is subscription access. And as I remember, you can access all the open access data sets. Now, if you want to submit a data set, what you have to do, you have to click on the submit data set tab. And then there is a form will pop up. You have to enter that form. You have to enter the metadata and to submit. Once your metadata is removed, you will get an submission where you can upload your data set. And then your data set will be published with the new format. So that UI is set. So anyone who wants to use your data set, they have to cite that particular UI. Suppose in the description you are mentioning your research papers which you want to cite, you want them to cite, they will have to cite them also. Okay? Another thing which Data Board is actively doing is competitions. So there are different type of competitions are happening throughout the year. These competitions are either organized by different organizations, different student branches or sections, or even data code owner as well. So as a data code owner, if you want to organize a competition around the data set, that what you can do using the IEEE data code platform. You don't have to go to some other platform to announce that competition, to host that competition, you can do it here. Then we have a search tab which you can use for searching any particular type of information you're requiring. So this is it's very simple uh, platform where you can access everything very easily. Now, I'll show you some different type of data use cases so that you can know how data sets are very important. You can see that quickly actually is reaching out to the people with your data set. So it's very easy to reach out to people. If you know that actually network is huge and actually branding is huge. And because of that, whatever work we are publishing with the IEEE, it will get a very good response. So you can see this. This is a 3 months old slide. So the number you can see on the screen are actually 3 months older numbers. And now after 3 months, it will be this number would have been increased exponentially. So this is one of the darkest data set submitted by um, researchers from the Technical University of Munich, and it is 60 hertz gigahertz FMCW radar gesture data set, and this data set is published with the increased acceleration in the gesture recognition using the AI. So this is one example. Another kind of data set. It is also one of the recent data set, not very old, and it is having very good number of downloads. So unified multimodal network intruder detection system. So you can see that we have this another kind of data set that is intruder detection system, and that particular data set we can see. We have another image data set that is published by Salmons University and US Forest Services. Fire Forest is creating a very adverse effect on our climate, and that's why for prevention of that, various kind of data sets have been submitted on IEEE data port as well. This is another, these are some few examples of different kind of data set which you can submit, and you can see that, overall structure, how these data sets have been, mentioned on our website. Now look into the contest part, because as a researcher, as well as a student or as a professional, either you want to participate on the competition or you want to host a competition around your data set so that maximum people can use it, can get benefited, and can support or can contribute on the solution which you are looking for. So this is one competition which was organized by IEEE Censor Council with their flagship event at Singapore, IEEE Flips conference, and this was a wearable health hackathon. So students have developed different type of solution on the given data sets. So some data sets have been given to the students. The registered student got the complete data set, they worked on it, they submitted their solution, and after proper judgment, few of the participants got the prize money as well. So now what are the basic benefits? So why we are doing research? We want to do research to get good solution for a particular problem. While we are doing research, we want to have global exposure of our research. We want to show this to the world. That's why we are here in the conference, so that we can see others' work, what they are doing, and we can showcase our work, what we are doing. So one is global exposure. Second is if you want to approach to the funding agency, and if your work is published in a renowned platform, it will definitely help you. You will get more citation when you are publishing your work with the renowned journal, conference, etc. And similarly here also, you can get more citation with your data set. How? So when you are making a data set, definitely you're providing one solution for a problem. So that solution you are presenting as a paper to a conference like this, or maybe in a journal. And after that, what about data set? You may upload it somewhere. So in place of uploading it into the some XYZ platform, what happens if you submit it to the IEEE data port? Like in IEEE data port, it will be published with a DOI. Having a DOI means whenever anyone is using your data set, they have to cite it. And when the DOI is available, citation of your work is very easy. So now with one work, you're getting 2 citations, one for paper, one for data set. Now third citation, you can write description about your data set and submit it into IEEE data description. So IEEE data description, you will get another citation, right? So in this way, you can have lots of opportunities for collaboration. You're getting storage space. Yes, a very good storage space. For a single data set, as an individual user, you can get 2 TB of data storage. It means you can upload one data set as big as 2 terabyte. So that is a huge space, I must say. If you're working, even if you're working on hyperspectral images, high dimensional images, then also 2 TB storage is good enough to serve the purpose. Now, what is the main role of high quality data set in AI-driven projects, any AI-driven project? So yes, the quality of data matters a lot. So we have heard this phrase very often, that garbage in, garbage out. Yes, it is true. So we have to have a good, well-curated data set, which is clean, which is representative, which reflects the target population to avoid bias. It is well documented. The metadata, label, context, etc. are clearly available. And then it will be easy for you to choose a particular data set and use it. So what are the different quality check? We know that very well. It should be clean, it should be creditable, it should be calculative, it should be complete, and etc. So there are so many parameters by which it is actually a good and reliable data set.
So if you are having a reliable data set, definitely you can provide a reliable solution to a particular problem. So IEEE Data Port will support your project in delivering a good, reliable solution. So how? So you can host, diverse peer-reviewed data set competitions. You can have different diverse peer-reviewed data sets available with you, which you can use in your project work. You can have reproducible link of the data set. It means if you are interested, you can collaborate with the author because author details are given, and then you can do some collaborative work. If your institute is subscribing to the IEEE data port, you are going to get, it means your institute or your company is going to get 10 terabyte of data storage space. And this is actually very, very good storage space. So the management of the data, you're free from this hassle of managing your data on a particular platform. In place of that, you are actually working on the your work without hassle and without any kind of worries. So, what are the different challenges and best practices? We know it very well that with the if you have a small challenges having a small data set, it will create overfitting. If we have unbalanced data set, it will create biasing. So that's why having a good balanced data set is important. What are the best practices you can do as a researcher? So you should use a reliable platform. One of the example is IEEE Data Port to access validated data sets. It leverages data competitions to crowdsource the robust solutions for your problem. You can have, FAI principle that is findable, accessible, interoperable, and reusable. So yes, all the data sets follow this principle, and that's what is one of the benefits. So there are various cases are there. I will not go into it much because we know that what are the consequences happened when the data set was actually biased. Very well-known example, most of you are aware about that IBM Boston a data set, which was a disaster, same as Amazon's biased hiring tool, which created a very aggressive buzz among people, and that's why we need to have we need to have a good validated and curated data sets. These are the basic information which I wanted to share. It's free for all IEEE members who are having this. If not, then you can directly take the membership of IEEE Data Port. It's just very minimal amount. If you are taking directly membership of IEEE Data Port, you can access all the data sets. Please open access data set, subscription data set, and every data set. So a complete data set is usable. All 9,000 plus data set, it's available for you to download, to work on it, etc. But yes, we need to cite it. So these are the different domains. And we different key takeaways that it is a one-stop data hub. It is a trusted AI research data set. We have more than 3,000 plus peer-reviewed data set. It is a data innovation. It means we are hosting it, you can cite it, etc. And it is cost effective and secure, where you can reach out to us. You can connect us on LinkedIn. You have my email ID on the first page, so you can mail me. You can connect me on LinkedIn. You can connect us on LinkedIn on IEEE Data Port. If you have any query, we are most happy to help you. Thank you so much.
Thank you so much, Dr. Anjali. And now we'll proceed with the lunch. Before lunch, I again want to announce that you can found IEEE Data Port outside. Their stall is there outside. If you're interested, you can go and visit the booth. And now we'll proceed with the lunch. I request everyone to please have lunch. And yeah, I also want to mention, Temi, that now it is moving out. It will not be here. It will be moving. So thank you, Temi, and thank you, Mr. Saurav, for bringing Temi here. It was great anchoring with Temi. Thank you so much.
Thank you, everyone. I'll be heading back today, but I sincerely thank the Earth Sense team for inviting me to co-host alongside Sushmi. I look forward to meeting you all again soon.
Thank you all. Thank you so much. Thank you, Temi. And you can collect your coupons at the counter. Thank you all. Enjoy your lunch. Thank you.